Have you ever tried to bend a piece of metal, only to have it snap like a dry twig? Or maybe you've destroyed a brand new drill bit trying to machine a piece of steel that felt harder than it should? That's because metal has a memory. Every time you bend it, roll it, weld it, or machine it, you're introducing stress inside the material. Today, we're talking about metal's reset button, annealing. Now first, let's clear something up. Annealing is not just heating metal. It's a controlled heat treatment process that changes the metal's internal crystalline structure, what you could think of as its internal DNA. At the microscopic level, metal is made up of crystals called grains. When metal is cold-worked, bent, rolled, stamped, hammered, those grains become distorted. Dislocations build up. Internal stress accumulates. Annealing reduces those dislocations. Think of it as giving the metal a deep structural massage. It relaxes the internal stress and restores ductility. And at its core, annealing is about managing one critical trade-off: hardness versus ductility. After annealing, the metal becomes softer, more bendable, and far less likely to crack under pressure. So how does this reset actually happen? Annealing isn't random heating. It follows a precise three-stage process. Stage 1, recovery. We begin heating the metal, but not too aggressively. At this stage, internal stresses start to relax. Atomic dislocations begin rearranging themselves. The grains haven't changed shape yet, but inside the structure, tension is being released. You can think of this as the metal loosening up before a workout. Stage 2, recrystallization. This is where the real transformation happens. The metal is heated above its recrystallization temperature, but still below its melting point. Here's what changes. The old deformed grains disappear. New, stress-free grains begin to form and grow. It's like tearing down a damaged neighborhood and rebuilding it from scratch. Clean, organized, and stable. This is the true structural reset. Stage 3, grain growth. Finally, cooling must be carefully controlled. If the metal cools too quickly, new stresses can form. If it cools properly, those new grains fully develop into a uniform internal structure. The result? Stable, consistent, workable material. In short, relax stress, form new grains, lock in structure. Now that we understand how it works, let's talk about why it matters. 1. Restores ductility after cold working. Cold working makes metal harder, but also more brittle. Annealing reverses work hardening. It reduces hardness, restores ductility, improves formability. Simply put, it makes the material workable again. 2. Improves weld zone performance. Welding creates extreme localized heat. In steels, this can cause brittleness in the heat-affected zone. Annealing restores uniformity and improves toughness around welds, reducing the risk of cracking. 3. Enhances electrical and magnetic performance. By reducing crystal defects, annealing improves conductivity and magnetic properties. That's why it's essential for copper components and electrical steels. 4. Eliminates residual stress. Machining, forging, casting all introduce internal stress. If left untreated, that stress can cause warping, cracking, and dimensional instability. Annealing allows atoms to migrate and relieve those stresses, improving long-term stability and reliability. Annealing isn't a single process. There are multiple types, depending on the material and the goal. Let's quickly go through the different types of annealing. Diffusion annealing, used to improve chemical uniformity. Atoms diffuse to eliminate segregation in alloys, resulting in a more homogeneous structure. Stress relief annealing primarily reduces internal stress from welding or machining. It doesn't drastically alter the structure, but it prevents warping and cracking. Normalizing, common for steels. Heated and then air-cooled. This refines grains and improves strength and toughness. Spheroidizing, used mainly for certain steels. It modifies carbide structures into spherical shapes, improving machinability and ductility. Incomplete annealing, heated below full recrystallization temperature. Used when slight softening is needed without completely altering the structure. Full annealing, heated fully to transform the microstructure, relieve stress, and significantly soften the metal. Common for carbon steels. Recrystallization annealing, focus specifically on forming new grains after cold work to restore ductility. Isothermal annealing, held at a target temperature for an extended time, then cooled slowly for highly uniform properties, especially in alloy steels. Different methods allow manufacturers to fine-tune ductility, strength, and machinability. What are the downsides of annealing? Of course, no process is perfect. First, annealing is time and labor-intensive. The full cycle can take several hours. Second, overheating is a risk. Too much heat can cause excessive grain growth and reduce hardness. Third, its effectiveness is limited for certain high-alloy metals. Despite these downsides, annealing remains one of the most important heat treatment processes in manufacturing. The key is proper control. A reliable manufacturing partner can carefully manage temperature, time, and cooling rate, maximizing benefits while protecting part quality. If you're planning a project and aren't sure about material selection, machining processes, heat treatment, or surface finishing, we can help. RapidDirect provides one-stop manufacturing solutions tailored to your budget and performance needs. If you found this video helpful, don't forget to like, comment, and subscribe. We'll keep bringing you deeper insights into manufacturing, material science, and real-world engineering.